It's a great pleasure to have Priyadarshi talking about Hilbert space and holography of information in digital quantum gravity. So these are first of the set of 2 lectures.
Hi, thank you. Hi everyone. Thank you for being here. So before I start the talk, I would like to thank Aninda and Orno for inviting me to give these lectures. So I'll talk about the Hilbert space and holography of information in digital quantum gravity. So my talk will be based on these 2 papers. There are other papers which I will mention in due time. So here are my plan of this first lecture. So first I will cover few basics about digital quantum gravity. Then I will solve the constant equation in the quantum gravity and I will give you the solutions. I will interpret the solution space as some theory space. I will tell you what theory I mean here. I will also introduce another basis in the Hilbert space which we call small fluctuation basis. This will be useful for computational purposes. And also I will review some old construction by Higuchi. Higuchi constructed some digital invariant states, and I will tell you that our construction you can think as some gravitational generalization of Higuchi's construction. So this is the plan for today's lecture, and in the second lecture which will be on Friday, so I have given a description of a Hilbert space. Then in the next lecture I will give you a inner product in this Hilbert space. I will also apply our formalism to understand cosmological correlator, and I will tell you that they obey some miraculous property called holography of information, and then I will give you a broad outlook of this program and what are possible future directions. So let me start. So you can stop me at any time to ask questions. So let me start. So let me tell you why like digital quantum gravity is like important to understand. So as you all know, like holography is a very novel feature of quantum gravity, and it was first realized by Maldacena in this ADS-CFT conjecture, but the calculation was done in a string theoretic setup. So what does it say? It says like a d plus 1 dimensional gravity dynamics can be understood from a d-dimensional non-gravitational theory. So you can think this is my bulk theory, and there is a corresponding boundary theory which captures the gravitational dynamics. Now the question is, can this holographic feature be understood without help of string theory, without going to the detail of string theory? Can I comment about this feature? The answer is yes, we can, even without string theory. We can understand in canonical analysis of quantum gravity. So yes, there is this question about theories UV completion, but without worrying about that fact, one can comment about holography, and in this direction, Shufrat and his collaborators, they devised a principle. This principle is called holography of information. No, actually, yeah. Actually, there will be no non-gravitational theory when in this say there is only one theory. I'll tell you. The good question. So they devised a new principle which we call holography of information, and they say that the information in a bulk of a Cauchy slice. So you can think Cauchy slice as some constant time slice. So they say the information in the bulk of the Cauchy slice is already available in its boundary. And yes, it is important to note that we don't talk about the dual boundary theory. There is only one theory, which is the bulk theory. And here in this principle, holography is a statement of redundancy of description in quantum gravity. Like this, it is redundant, like this bulk information is already present when the quantum gravity is switched on. So this is this principle. Now, to make it more precise, like what they do, So let's say we have some boundary operators here in the Cauchy slice. So let's say we have some O1, O2 dot ON. So what they devised, they said that you can actually distinguish between two different states using these boundary operators, sets of boundary operators. In that sense, all the information of your bulk is already available in your boundary. So now this works well when your Cauchy slice have a boundary. So this works well for ADS, like asymptotically ADS, asymptotically flat space, because their Cauchy slice have a boundary. Now what about global de Sitter? So I will introduce you what de Sitter space is for the time being. Let me tell you that global de Sitter, the Cauchy slice is compact. So now there is no boundary of your Cauchy slice. So what is the fate of this holography of information in de Sitter space? That is one question we are asking. Okay. Now, this is one motivation from the holography perspective. But de Sitter is interesting in its own rights because de Sitter is close to the real universe. Because we know that our universe is expanding now, and also it was expanding in its very early stage. So one can model an expanding universe with the de Sitter spacetime. So de Sitter is interesting from this reality perspective. So now, now we will be studying this holographic setup in the de Sitter quantum gravity. Okay. Okay. And also one point is that this holographic principle, this is only true when you are switching on quantum gravity. I will come into detail what I mean. Like this statement is not true for any gauge theory or any other theory. Like so far it has been checked, like it is only true for quantum gravity theory. Oh. No, we actually don't go into that detail. We assume like, okay, if one gives you some full UV complete theory, like what like the understanding will be still true, but as we do not know any UV complete theory, even from a low energy effective point of view, like this principle holds true. Okay. So now, okay, let me now introduce you to the de Sitter space. Yeah. So I will talk in the de Sitter's perspective in the second lecture. So today, so this is my motivation. So we want to study de Sitter quantum gravity. One motivation is, okay, de Sitter is close to reality. We should understand it more detail. And another motivation is what will be the fate of holography in de Sitter, because this holography is only true in quantum gravity. So that's why we will be studying the quantum gravity in de Sitter. So before that, let me introduce you what is de Sitter space. And I will also tell you what I mean by quantum gravity here. So a d plus one dimensional de Sitter, you can think this is a hypersurface embedded into one higher dimensional Minkowski spacetime. So let's say you have this M1 d plus 1, which has this metric ds square equal to minus dx0 square plus dx1 square d plus 1 square. Now you take a hypersurface in this Minkowski space, which define my de Sitter space. So the hypersurface is x0 square plus x1 square x d plus 1 square equal to some radius, which we call de Sitter radius, and which for this purpose of the talk we'll set it to 1. Now this hypersurface defines my de Sitter space. As you can see, like this surface actually preserves this isometry group. The isometry group is clearly SO1, d plus 1. And if you put this if you put this metric on the de Sitter space into Einstein equation without matter, you will get some positive cosmological constant, which is in our notation, it is just d into d minus by d into d minus 1 by 2, which is greater than 0. And so this is some classical de Sitter space description. There is no matter or anything. Now one can parameterize this de Sitter space in various parameterization. So one convenient choice is global de Sitter. And we choose this x0 as some sin h tau omega, sin h tau, and then there is this xi is some cos h tau omega I. This omega is some d-dimensional sphere coordinate embedded into one higher dimensional Euclidean space. Now you can write the metric here with this global de Sitter, which is just d square okay. Now let me draw a picture for you how to visualize this global de Sitter. So as I was saying, you can visualize this with going to one higher dimensional space. And so this surface of the hyperboloid, you can think this is some de Sitter space, and these constant time slices are like this. These some constant time slices, which you also call Cauchy slice. And as you can see, this Cauchy slice or constant time slice or the spatial slice, the volume is a function of your time, of your tau. So like it is increasing here, like so this as you take tau goes to plus minus infinity, this volume actually becomes very large. At this very late time and very early time, the volume becomes very large, and del tau is not any vector. No, this is my definition of de Sitter space. I am defining my de Sitter in this way. No, I think he asks like, is there a reason so that we are embedding de Sitter into Minkowski? Yeah. Okay. So this is some basic classical definition of my de Sitter space. And one thing you have already noticed perhaps that yeah, the time is here tau. Yes, yeah, thank you. And when as you have already noticed that for tau greater than 0, this volume of this Cauchy surface or the spatial surface is increasing. So you can model an expanding universe with this model, with this de Sitter space. And when tau is very large tau and tau greater than 0, so you can think like this cos h tau now goes as some e to the power tau here. So it is the size of your universe is like exponentially increasing. So now this is the classical de Sitter space. Now now we can put some matter with it, and we can write a generic Einstein equation in de Sitter space. And this is a standard Einstein equation in de Sitter space. And for simplicity, we will only take like the matter, which is like minimally coupled scalar. This is just scalar matter. Now this is some classical setup. We did not have any quantum mechanics here up to this point. Okay, because when I will everything then I will do in d dimension. So for d dimension I will not use any hat. So this will be very temporary. This is for only a few equations. So I put a hat there. So now the question is, we will do quantum mechanics in this setup. And now the question we ask, what are the quantum states? So what are the quantum states in this setup? And when gravity is on, dynamical gravity is on. So let me tell you into a more detail what I mean by when dynamical gravity is switched on. So this you can study like quantum field theory in fixed de Sitter background. So I have written this de Sitter metric. You can study quantum field theory in the fixed de Sitter background, but that is not what I mean by like quantum gravity in de Sitter. Yes, sure.
So instead of global de Sitter, suppose we use this Poincaré patch or this.
Yeah, Poincaré patch. Yeah, that's like people use for studying cosmological correlator. But the point is here that we know that de Sitter is actually have some compact like Cauchy slice, but it's not very evident from the Poincaré slice.
Right.
So maybe our understanding is maybe you have to put some boundary condition on the boundary of your Poincaré slice to like understand this constant analysis there. But we are not sure. It's I don't know anything much.
But then the activity of analyzing cosmological correlators is to do the calculation on the Poincaré patch.
Yes, yeah, that I agree.
Impose a boundary conditions for the vacuum.
Yes. But I am saying for the constant analysis, one of the point of this this constant is that in de Sitter, your Hamiltonian is 0. The bulk Hamiltonian is 0. There is no boundary, as you can see in these global slices. There is no boundary of your Cauchy slice. So your bulk Hamiltonian is always 0, and that imposes some serious constraints on your Hilbert space. So, but you can do the same thing in Poincaré. But now you can think, but you see that Poincaré might have some boundary. So we still don't know like how to analyze this constraint in this Poincaré patch.
I see, but the constraints that you're going to talk about will, in principle, constrain correlators in the global.
Yes, correlators in these, like what I will talk about, like this constant, we'll find some states which obey these constraints, and the state we'll find at very late time slice here.
And those will coincide with what people study in cosmology?
I will tell you, like I will in the next talk I will tell you like how to interpret that cosmological correlator in our setup. But what you can think, like if you take your time like very large, the Poincaré slice and the global slice, they actually like coincide, like so yeah. But yes, that is true. The question was is like we still don't know like how to impose these constraints on the Poincaré slices, because it seems like there is a boundary there, but we know like in de Sitter always the Hamiltonian is 0. So yeah. No, the Cauchy. I am saying this. My de Sitter is the surface, not the bulk. So your Cauchy slice is just some circle, some HD. So HD doesn't have any boundary. It is just some compact slices. Okay. Thank you for the questions. Okay. So now what I am trying to say that we are not interested in studying quantum field theory in de Sitter background. Like when people study cosmological correlator, they only study some quantum field theory in the de Sitter background. But we are not interested in that. We are interested in quantum gravity, and we are allowing the metric to fluctuate. So this metric, it is some de Sitter metric, G mu nu de Sitter, plus there can be some fluctuation. Now we are taking a notion of asymptotically de Sitter space. What does it mean? Like if you wait long enough, like if you go to very late time or very early time, the metric should look like this de Sitter metric I have written earlier. So this, in this sense, we are studying asymptotically de Sitter space. We are allowing metric to fluctuate in the bulk, but it will be the same de Sitter metric I have written earlier at this point and this point. Now, when we are saying
People also study fluctuations of the metric in the Poincaré patch.
Yeah, but that is you can think still like I don't know like whether they impose the constraints. Also one point is that they only work with this Hartley-Hawking state. Hartley-Hawking state always obey the constraint, but there can be some other states. Like people do not comment about that. Like if you put some operators on top of Hartley-Hawking, those states are not going to satisfy the constraints. So they are not states in a de Sitter quantum gravity. Okay. I'll come into detail like what I mean. Okay. So now, we are. What I am saying. So we are allowing metric to fluctuate, and also we have some constraints. Now, now these constraints, like these are like, you can think these are like some Gauss law of your EM theory, and in gravity there are these local diffeomorphisms. And which is some local gauge symmetry that gives rise to this constraint. And schematically, you can think classically, these are some equation of motion which actually put condition on your initial slice. If you give me some Cauchy slice, you have to fix some initial data there. So these constraints, they put some condition on your initial data. And this is the classical statement. Now, if you switch on quantum mechanics, Dirac told us that you have to impose this constraint on your physical state. So we will call these guys psi qg here. Now, as you can see, it is very non-trivial whether if you take some state, like the Hartley-Hawking state, the vacuum state, they obey this constraint because it is a vacuum, it should obey the symmetry of your theory. But the point is, if you put some arbitrary excitation on top of this Hartley-Hawking vacuum, they are not going to satisfy the constraints. Okay. So the question we ask in this talk. Yeah. This is just G00 and G0I. Yes. I'll come into detail. I will try to derive this thing, but if time permits, okay. So now so the question we are asking, what are the states? Because if you take some QFT states, these are not going to satisfy these conditions. Now I will tell you what are these constraints. So, as Justin was saying, these are just some equation of motion, but this equation of motion should be interpreted as a constraint, like they are putting condition on an initial data, they are not evolving the initial data. So, there are various ways to do this thing. One particular way to do this thing is like using this ADM formalism. So, I will give a very brief detour, like some 5 minutes detour of what this ADM formalism is and how we get the constraints. This is very like known topic, people know all these things. So now like let's take our de Sitter spacetime here. We put some like we are choosing some arbitrary coordinates in de Sitter d+1 and the metric is g mu nu hat. Now this ADM told us to foliate the de Sitter spacetime with some sets of hypersurfaces. Like we choose some hypersurface here, and each hypersurface we are giving some, we are putting some scalar function. We are labeling them with some scalar function t. So from each hypersurface to another hypersurface, the t value changes. So it is giving you some notion of time evolution. So if you draw one like curve like this, some t curve. This t curve, along this t curve, the time value will change. It will give you some notion of time evolution. And let's take a particular surface here, one particular like t surface. And what you can do, you can introduce another set of coordinates here, which is, we are calling it xi. Now I have introduced some coordinate, some t and some xi. So this you can now this you can think like some sets of arbitrary coordinates here in de Sitter space, because we will be studying the quantum de Sitter soon. So this original coordinate system, like I wanted to say, like it is some generic coordinate system we are choosing. Okay. Now just 1 minute. Yeah, so now we are choosing this foliation to be very generic. So that means this t curve here, like it can have some component along this tangent to this surface and also to this normal to this surface n mu, like e mu I here. So we are choosing a very generic foliation of this space time, and we can write t mu as some n mu plus ni e mu I. So this object, like this e mu I, this is the some projection operator which projects onto the hypersurface. This is the tangent to the hypersurface, and n mu is my normal here. And I have chosen some coefficient. This t curve, this tangent vector to the t curve has like some coefficient here, this n and capital Ni, and I am telling that I am naming this guy as some lapse function, and I am telling this guy as some shift function. And with this, you can actually write, relate the dx mu here to this t, and what you can write that the metric becomes some minus n square dt square plus gij dxi. Okay, so this is called idiom metric. Yes, sure. So T mu is the tangent to this T curve. So I was saying I was foliating this space-time with some particular scalar function, and so you can draw some curve along which the T value changes. And I am okay. So sorry, I did not draw it. So this is my T mu here, the tangent here. We are decomposing the tangent into this n mu and e mu I, and the coefficients are capital N and capital Ni. So so now with this we can actually write everything, this d plus one dimensional dynamics, into these new variables. So earlier we had some metric g mu nu hat. Now we can write with this n and ni and gij. So this gij is my spatial metric. Gij is this metric on these slices. Now what one can do, one can actually start with some Einstein-Hilbert action in de Sitter space-time, which is some 2 kappa square d plus 1 x hat r hat minus 2 lambda, plus there can be some given sucking term. So this is in terms of the g mu nu hat. Now you can write this thing with the new variables. Then my new variable is my n, and then this ni and gij. And what you can do, this is some dt 1 by 2 kappa square d dx square root of g times n plus there are some given sucking term. Okay, so what I have used here, I have used some Gauss-Kodachi equation to write a d plus 1 dimension curvature scalars in terms of d dimension curvature scalars. So up to this point, this is like very generic thing. Now from the action, what I find that there are some constraints in this dynamics. What are these constraints? Let me delete this part. So as you can see, now my variables are what? Gij, n and ni. But if you take that action and you do this guy, like n dot, which is my pi n, the canonical momentum corresponding to the n variable, you find that this is 0, and also you can find pi ni equal to del s del ni dot, this is also 0. So as I was telling, now my initial data actually comprises with this pi gij, its canonical momenta pi ij, this ni, its canonical momenta pi ni, and also this n canonical momenta pi n. But these constraints are saying we cannot impose like this initial data on a surface freely. We have to obey this constraint pi n equal to 0 and pi n I equal to 0. So given a Cauchy surface, these are my constraints. And now what one can do, okay. Yes. Yes. Now I have removed all the hat. Everything now will be in terms of the metric on this surface, this Cauchy surface, spatial surface. Yes. How much time I have? Okay. So now. Okay. Yeah. Kij is my extrinsic curvature, which will be I related to my momentums. So okay, I don't. So these are okay. I don't remember it now, but this will be related to this Lie derivative along this normal of this Gij. This will be related.
Pullback of the symmetrized covariant derivative of the norm.
Yes. Like how these surfaces are like embedded into one half dimensional space. This is it. Now you can write Hamiltonian like this. This Hamiltonian will be d dx sigma and then square root of g in curly h plus ni curly hi. So now you can actually do this same Lysander transformation to get the Hamiltonian here. Now we have these constraints here on a particular surface, and we want these constraints to be like preserved by the Hamiltonian flow. So that means like we take this h and we take this pi n, which gives this curly h equal to 0, and also similarly we get curly hi equal to 0. Okay, so this we call Hamiltonian constraint. And this called momentum constraint. So now as you have seen that now we are putting a curly h equal to 0, curly hi equal to 0, that means Hamiltonian is just 0. So as I was telling, like there is no boundary of global de Sitter Cauchy slice, so there is no boundary term. So there is a big difference between de Sitter and this ADS spacetime. Like in ADS, what happens? Like you have a boundary. So your Hamiltonian is a boundary term, and so you have a good time, which is a good killing vector there also. So you can understand your bulk dynamics from a boundary perspective, from a boundary time. But here there is no time here. What I mean, like the standard time, the canonical time here, what I defined with this foliation, etc. This canonical time is not a good time because under the evolution operator, the h is just 0. So you can think like there is no evolution of these dynamics here. So one of these, like you will see soon, like we need a good clock to understand the dynamics here. I will tell you some good definition of clock which we used in our setup soon, but for the time being I am saying like t is not good time coordinate. Okay. Yes.
Suppose if you had only flat space with dynamic gravity, what would have been the status?
No, for flat space also you have this boundary term. You have the flat space, you have a boundary term. So the time is a good time coordinate there. But the global de Sitter is really problematic. And the Poincare-Apache, I really don't know because it seems there is a boundary, but it should not be there. I really don't know that part. Okay. So now, so these are, everything is still now classical. There is no quantum entering here. Now, we want to study quantum mechanics. So in quantum mechanics, there is we will deal with states. Now there is some alternative description of states in terms of wave functionals. Now these wave functionals are like analogous to wave functions in quantum mechanics. Like say given a Cauchy slice, we choose some good operators, Xi, such that we know its eigenspectrum here. So that means we can define some new basis by taking this inner product with this Xi kets, which we define some psi Xi. So these Xi's are what? The Xi's are field living in this Cauchy slice. So now we can write some wave functions which are like some function of existing fields. The existing fields are my metric, my scalar field, etc., etc. Okay. So I will take this language because it will be easier to understand the problem here in this language. So now we go back to our question 1, like what are the quantum states? And I was already telling you that we have to impose these constraints. So what are these constraints? The constraints are this pi n equal to 0, pi ni equal to 0, curly h equal to 0, curly hi equal to 0. These are my constraints. So let me solve it. So we want pi n equal to 0, pi ni psi equal to 0, curly h psi equal to 0. Okay. Now, in this canonical analysis, you can think this pi n is actually some del del n of psi, and this is some del del ni of psi. Okay, so you can just solve these constraints by restricting your psi as not function of n or ni. So let's say psi is also what are my variables here? My variables are my n, ni, gij, and maybe there's some matter field chi. So I am saying that these constraints can be easily solved. You can just take psi as a function of the other field, not of n or ni. Okay. Now comes, let's say, this momentum constraints. I will tell you later, but as you can already see, like this hi actually comes from some special diffeomorphism invariance. I will come into detail, like how this really comes. But for the time being, believe me that this actually comes from the special diffeomorphism invariance. Like one comment is here, like this h or hi, like how this arises, why these constraints are there. This is because this gravity has this local diffeomorphism invariance. The curly h corresponds to that we can choose any n. Our all this dynamics we are studying does not depend, should not depend on your choice of n, and that's why we are getting curly h equal to 0. And also the same with the ni. Ni is like my the special diffeomorphism degrees of freedom you can think of. So we can solve these constraints by choosing a wave functional which is special diffeomorphism invariant, and that is like pretty easy. So this is also we can try to solve, but the real tough question is how to solve this curly h psi equal to 0. People also call it Wheeler-DeWitt equation, here bearing the name of DeWitt. So this is the question we are asking: what are the quantum states in the de Sitter quantum gravity, and we want to solve this equation, the curly h psi equal to 0. Any questions so far?
This Hamiltonian, you don't bother to satisfy all the Hamilton's equation, like h comma n gives n dot.
Huh.
How will it satisfy this? Like usually in Dirac's theory you add an improvement terms, right?
No, but
h comma n, n dot, that's the Hamilton's, the other Hamilton. N is the coordinate. So h comma n gives n dot.
yes.
So how does this happen?
No, but here there is no n dot in your like.
Yeah, so but usually Hamilton satisfies that. H comma pi gives pi dot.
Yes.
H comma n gives n dot.
Okay. But okay, maybe you can think. Okay.
There are pairs of equations.
Okay. Yes. Okay. Okay. At this point, okay, I do not know.
Usually there are improvement terms in Dirac's theory.
H comma n should be pi, it's the conjugate.
N dot, d by dt of some object is h comma n.
Right, sorry.
So usually there are improvement terms.
Okay.
In Dirac's theory.
Okay. Okay. As of now, I don't remember it.
This is the naive Hamiltonian.
Yes.
Dirac's theory is the naive Hamiltonian. And then you have the improvement.
Okay. Okay, as of now I don't remember it, but okay, maybe we can talk about it later. Okay, like I wanted to say, like here there is no n dot in your action. Okay, n dot is 0. Okay, I think there are some. Okay, I am not sure about this. Okay, I am not sure. Sorry. Okay, maybe I can talk about it later. Okay. Okay. Now, as I was saying, we want to solve this question, but the point is, like this n or n dot will not like enter into this constant. Like we are forgetting any depend. Yeah, the function. Yeah.
But you were talking about the zero, so I was wondering, is there something else?
Okay. 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 Okay.
So far, whatever you presented seems to be standard. So
Yeah, this is standard.
is this something? I mean, it's something people must have done.
Yeah, this is known. This is known. No, no, yeah, this is just I want to set some background. Yeah, that's yeah, yeah. That's okay. These are all known. Yeah. So now, just now the question comes. Now we want to solve this guy. Curl H psi equal to 0, and now I am telling you this vacuum, Hartley-Hawking vacuum, is my solution, and you can think this. You can get it with some some action. By integrating over all the possible manifolds which has only one boundary, and you specify your metric and scalar field at this boundary here, and there is no boundary here. That's why it is called some no boundary wave functional. And like schematically you can write this like this. And now I am telling you that this psi HH measure is, you can put some dg. But this is the full G. I means like it is not the, it contains all the A and Ni everything like here. And also you can put some d chi. I am putting a G tilde here for that, or maybe G hat. And now I am telling you that this del psi 0 or del psi HH, del n is 0, and also same for del psi Ni H is 0. And if you take some n del n here, that will bring some del s del n, and the del s del n is basically this curl h and curl hi. So that will give me psi hh equal to 0. Okay, this is fine. So I am telling you, okay, we know one solution, which is the Hartley-Hawking wave functional, which is over the constants. Now the real question is, put some excitation on top of it. Make some state with some, you can do some smearing also. You take some metric, some g x1, g xn, and then you put some chi y1, chi yn, and you take this psi hh. So you take this Hartley-Hawking state which satisfies the constant, and you impose, you put some excitation on top of it. You can also smear with some good smearing function, maybe some square integral function. Now the question is, it does not satisfy the constant. It does not satisfy h psi equal to 0. And you can take some arbitrary superposition also. So still it does not satisfy. So the real question is, what are the states which satisfy? Is there only one state which satisfies the constraints, or are there many states? That is the question we are asking. And as you will see, like there will be some specific smearing functions, and there will be some specific superpositions for which this kind of excitation on top of your vacuum will obey the constants. And for that we have to really solve the constants. Okay. Okay. So I have, okay. Is this fine? Any questions so far? Okay. Cool. Okay. So now I am. Okay, so up to this point everything was very known, but we are asking this particular question: are there any more states which satisfy the constants? So this is my background up to this point. Now I will go to our paper, how we will solve these constants. Now, just for completeness, let me write the form of the constraint: 2 kappa square G inverse some Gij. Now this R is this special R. This is not the R hat of this full space time, and then there will be some H matter. I am not going to the matter part because for simplicity, also for the sake of time. and also there can be some interaction term. So we will take some minimally coupled matter, and there can be some other interaction term here. So this is my Hamiltonian constant. This H matter is just some T00 of matter. Okay, written in terms of pi and this pi chi and this chi variable. So now, as you can see, like this is a quadratic functional differential equation, and we want something like psi g chi equal to 0. So chi is here, this chi is here. There is also g here. Okay. So as you can see, this is very hard to solve. Like this is some quadratic functional differential equation, and we want to solve it. So, and there is some big issue of normal ordering also, like because there are some quadratic terms, we have to normal order them correctly. Now, you can solve it in some perturbative way. So you can choose some perturbation with this kappa equal to square root gn. You can choose some perturbation parameter like this kappa. Also, there is one good perturbation. What you can do is what we call this large volume limit. So this is some different perturbation, but not respect to the kappa, not respect to the g Newton. This is some different. I will tell you in detail what I mean by this large volume limit. Okay. So we are going to a limit where this curvature terms, the Ricci scalar, is very less than lambda. Also, there will be some potential terms in the matter, V matter, very less than lambda. Okay. So let me do a variable change. We are not taking a limit. Let me do a variable change, which is like omega ij. And as you know that this Ricci scalar of omega square gamma ij, I am taking the date gamma is 1 and is just related to 1 by omega square r of gamma ij. So I am telling you, now take a large omega limit such that this r of omega square gamma ij or r of g ij is very small compared to what? This compared to the cosmological constant. And you can also take the similar limit in the matter side. We are taking this particular limit. We are doing some, this variable change is some like easiest way to do this like calculation, like taking this limit. You can also do without the variable change, but it is very convenient to do it. Now, what we are doing physically here, like you can take some limit, but like what are we doing here? So as you know, like the volume of this Cauchy slice is related by this. This is some square root g, and as you have taken determinant of gamma is 1, this is basically d dx of omega to the power d. Now, as we are taking large omega limit, that means the log of this volume term is very large. And this is the volume of what? Volume of my Cauchy slice. So I have drawn the de Sitter space here. And we are going to a limit where the volume of the Cauchy slice is very large. Like it is here or it is here. These two limits. And I am claiming that in this limit, that ugly constraint actually becomes very simple and you can solve the constraints. Okay. So now there can be two limits, either very late time or very early time. We are choosing for very late time because it also corresponds to the real universe, etc. So also there will be some matter part here, chi equal to some omega to the power delta O. Like this chi also scales with this omega here, like with the volume of your Cauchy slice, and there is some operator O here. And so what we will do, we had this initial variable, the original variable gij and chi. We are going to some intermediate variable which is omega, gamma ij and O. So first we will change some variable, then we will take the large omega limit, and then we will solve the constraints. So that's my algorithm. And I will tell you that in this way you can actually solve the constraints and get some result. Okay, is everything fine? Okay.
Can I think of this? So you have a state, so I can take the expectation value of the metric operator with respect to the state. Can I think of this as being a probe approximation?
No, why do you say that? Can you please?
So you should be able to calculate the expectation value of the metric fluctuation in that state.
Yes, yeah.
For example, whatever the standard deviation.
Okay. Okay. So are you saying like this? You can take some exponential value of this operator.
For example, or maybe I meant the operator corresponding to the metric.
Like the Gij.
Yeah.
Okay. And
So I should be able to calculate the root mean square fluctuation of Gij with respect to the state.
yes.
So would these limits make sure that root mean square fluctuation is small? Because you don't want your root mean square fluctuation to be large either, right?
Oh, why not? Sorry, I am not understanding.
Because then wouldn't you actually need to take into account the back reaction?
Okay. Okay.
Yeah, maybe I'm confusing myself and confusing you. So.
No. Okay. 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 Now, what we are simply doing, like we are taking this. So okay, you can think just from this picture also. Like we are going to very large time, and in the very large time, the volume of your Cauchy is large, and that corresponds to this determinant of your like metric is very large. So, but I am not sure if you take expectation value of this. Like you can think. So one point is like your Hilbert space should not depend on like your slicings. The Hilbert space, like so, even if we are going to a very large time, you can complain like, are you losing some bulk dynamics, everything? But yeah, maybe we are losing the dynamics, but from the Hilbert space sense, this thing still is like very enough, like this for the specification of the states, like this description is enough, like even if you go to very late time. But yeah, I am not understanding the question, but maybe we can talk about it later.
Yeah, let me just try
Okay,
to
okay, sure. Yeah. So so this is our what we are trying to do. We will be we will be changing our variables Gij, chi to these intermediate variables. At the end, we will write everything in terms of the original variables. But we will be taking this large omega limit in the Hamiltonian constant, and also we will take some answers of psi in this large omega limit. Let me tell you what the answers we are taking. Okay. Okay, so I am taking an answer e to the power if, and where this if is something, if comprises with two series, x alpha minus 1 plus x0, and then there is another series y beta minus 1 and dot, and then there are some terms which goes like 1 by omega. As I was saying, like we are taking some large omega limit, and I am expanding psi in a large omega like limit, and this f is like sum over two different series, like this x alpha and y beta. So this xk terms, these are some functionals which goes like omega to the power k. And this yk, it also goes like some omega to the power k. You can ask why there are two different series here. So this part, this will be present even if the matter is not present, this x term. And this y part, they will appear only if there is some matter coupled with my gravity. And so this is my leading order term. We are just taking some like unsuch, alpha and beta are still undetermined here. We will determine those terms soon. So it is a very generic unsuch, and we are taking this thing, and we will be putting in the Hamiltonian constraints, and we will solve the constraint. Yes, sure.
Is it a sensible thing to ask what is the metric seen by these fluctuations? So it's a state.
It's a state. Yes.
And so there is a sense in which I can measure the expectation value
of the psi ij. Okay.
metric operator.
Okay.
With respect to the state.
Yeah, you are saying this thing. Okay.
So what is the answer to this question?
Okay. For that, I think we have to first define this inner product here.
Right.
We did not define an inner product in this space of states. We are first finding the states.
And so is the point that could be any arbitrary number, or is there some way that you are keeping these things finite?
Okay, so.
What guarantees that this is normal? What guarantees that this is?
Okay. So there will be some. Okay, when I'll be giving like talking about in the second talk. So we'll give you some prescription of the inner product that will give you these correlation functions in general, any correlation function, and there will be problem with some zero modes there. And the zero modes you have to fix by putting some insertion, extra insertion. So I will tell you, like, if you have 3 insertions in your correlation function, those things are well different. This is just like the string perturbation theory, and for the other things, these are pathological. Maybe you can define something, but in general, like, as you have to fix the zero modes.
But this has to be a finite number, right? Because otherwise, this calculation does not make any sense. Because if the expectation value of the metric with respect to the state is not small.
No, it is not. Okay, I don't want to say it is not small. It is like ill-defined. I want to say, like, when I will be okay. No, I think you can define it. So there will be some other variables here, which we'll call some delta G here. I will tell you later. So you can fix some 3 points here also. You can fix 3 points here. So the point is, you can calculate any correlation function after 3 point fixing because of the zero modes. Just like we did string theory. So I think you can actually calculate the Gij here, but you have to take care of these point fixings.
And this is supposed to be finite.
Yes. Okay, I think people are now calculating this thing, like Tunir and Ashik. They are checking our formalism to explicitly calculate some cosmological correlator. I think their paper will be out soon. So I think So I hope this is finite. Like we checked, like this is finite, like in the sense like there is no problem about zero mode fixing or this volume of de Sitter does not come out anything. So in that sense, it should be finite. But I think for explicit computation, I think they're still checking. Yeah. Okay. So now. Okay. So now where are we? So how much? So we'll be ending at 12.
You can just end at a
normal time.
Some place where you feel logically.
Okay. Cool. Okay. Cool. So let me just give you one small example how we are solving this thing. So we have this Hamiltonian constraint, and this Hamiltonian constraint acting on psi. We're trying to solve this thing. So now there will be some kinetic term of the Hamiltonian constant of this equation. There is a potential term. Kinetic term means like there will be this del g, like pi is my del g, and etc. There's some kinetic term and there is a potential term, and we are expanding everything in omega. Now we will choose the power of omega. We'll choose the highest power of omega. We'll solve at that order. Then we'll go recursively, like 1 power down, etc. So this is some recursive structure there. We'll use that. So in this very leading order, omega to the power 2d 4d minus 1. So this is my very leading order solution. If you because this x alpha I claim like this goes like the highest power omega to the power alpha, and this is my kinetic part, and then the potential part it just goes like omega to the power 0. Okay, so better this term should also go like omega to the power 0. This is some term from this equation. We have this equation. This is the very leading order term. Okay, so now it should so alpha you can you have your omega to the 2d here. So you should set alpha equal to d, as you can see from the equation. Okay, because this omega cancels, so there is some omega to the power d. So it's better like the alpha should be d. Like that means x alpha goes as omega to the power alpha. I define my x as omega goes like omega to the power k. So this alpha should better be d here. And so you can actually solve this thing, x alpha or xd as minus d minus 1 kappa square d dx square root g. Now, if you are careful with this calculation, you see like there is a whole square here, and when I'm solving this thing, I choose one particular sign, and this sign actually corresponds to the negative extrinsic curvature, And that means, like in our definition, like we have defined extension with the minus sign. So in our definition, it corresponds to some expanding universe. So this, if you like calculate you can calculate Kij from here, and that corresponds to some expanding universe. So that's why we have put the sign here. Now you saw the structure. Now it is the leading order. Now you can go to one sublet. You can put back here. There is some recursive structure. You can determine x alpha minus 1 dot dot, and similarly you can determine this y beta, etc. But this recursive structure fails at some point, and that point is when we are trying to determine x0. Okay, so let me write the differential equation for x0. The x0 is kind of logarithmic. I will like x0 term. Like you can think it's logarithm. I will tell you why. So this.
Some of these terms become imaginary or something because you said psi is e to the power if.
Yes, psi is e to the power if. Yes.
Would it be just a phase or something? But and then you are superposing.
Yeah. So this f is my this x alpha. So these are all these terms. These will be my phase. All these terms will be my phase. Yeah. Yeah. And but there can be something like real from the x0 term.
Oh,
Yeah, because x0 is undetermined. Yes. Yeah, thank you for the question. Yeah. So now I just want to write the differential equation for x0. x0 here, and you can go back to the original variable. Like let's forget about omega. The purpose of omega is over. We can just go back to the original variable. Is some delta so this AD is actually some anomaly polynomial which is imaginary, and these are like non-zero for even d. Okay. So now the point is solution of this equation is not unique. I want to emphasize that. The solution of this equation is not unique because you can just add any special diffeomorphism invariant functional like with this, and that will be also my solution. Sorry, x0. So, this like I want to draw an analogy with the CFT partition function. You can think this is some like quote unquote CFT partition function because this anomaly structure is almost like weak rotated to the like event dimensional CFT, like this anomaly structure. There will be I, but apart from that I, the structure is almost like this event dimensional CFT, the stress anomaly term here. And so, you can think like this is my trace anomaly equation, but the trace anomaly equation does not say more about CFT. It can be any CFT. So that's why this x0 is not unique. Okay. So I will write this e to the power ix0 term separately. I will define a z here, and we can couple all these terms here with some phase e to the power is. Okay, and so this is my solution. Okay, let me delete this part maybe. This is for just like this graffiti, like this. Yes. Like there will be some like this. Okay, I can write the anomaly term. Just give me 1 minute. Yeah.
This is the analog of the ADS.
Yeah, there will be a central charge. This for 2D, there will be central charge. And you can think that central charge is just analytic continuation of Brown-Henner central charge. This.
Yeah, it becomes imaginary.
Yeah, you can think. I will just write the structure of A2 and just 1 minute. Okay. So you can think this A2 is just I by 2 kappa square root of GR, and then this A4 you can find this is some 16 pi square root of G minus AE4. This is some Euler density, and then there is some CW ABCD. this A and C are some I pi by 4gn. So if this term you can think, forget the I, this is this standard, the Brown-Heller central charge that appears in this like the 2D CFT partition function. Like if you take a Weyl transformation, under a Weyl transformation it gives you some anomaly. Okay, this is some Weyl anomaly I wanted to mean. Okay, this is some Weyl anomaly. Like under some Weyl transformation, this gives you some anomaly term, and that anomaly term is in our, like in ADS 2D CFT case, it is just the square root of g here. But what we are getting here, there is a I here. So it is some imaginary central charge there, or imaginary anomaly we have here. Okay. Is this fine? Okay. So now what I am telling you, that our states are something like e to the power is times z, and this z can be real. And one point is the s we have found everything like very local. The s, it is some like local, and this is very universal phase factor. But z can be non-local, z can be real, z can be anything. It is very non-unique. So now I will come into the like detailed analysis of z, because if you calculate some mods like wave function, like this kind of correlation function, like we will calculate some mod psi square. And in mod psi square, there will be entering mod z square only. So we will be interested in this quantity. So I will now tell you more about this z and how to like understand this z as some quote unquote CFT partition function. Is there any question up to this point? Okay. Okay. So I will tell you like why we are interpreting this z as some CFT partition function. Yes, but like if you like okay, so in the holographic renormalization like the thing, so what you do, you calculate some ADS partition function with the radial boundary condition, and there also you can take some like Weyl transformation there, and you get some anomaly, and you can think like our calculation as like some analytic continuation of this holographic anomaly calculation also, but we are solving everything in de Sitter. We are not doing any analytic condition, any fuzzy business or anything. We are directly solving it for de Sitter. And also in de Sitter, this is like more physical. Like I don't know what does this radial this, you have this radial slice and you have a Hamiltonian constant also, but the solutions is just some partition function, okay. But here this solution here are some state. This is some physical object. Like you can add states, you can do more things with the states. But here I don't know, this radial perspective, like these are not, the solutions are not like you cannot like interpret them as states or anything here. I want to say here it is more physical, like in this de Sitter perspective. Here it is some radial slices, and you put some Hamiltonian constant on the radial slices, you solve them. But here I think I am saying it is more natural here to solve Hamiltonian constant and find the states. Okay, so let me write down this the equation for Z's. Okay, so we have started from this thing, h psi equal to 0, h I psi equal to 0. Yes, sure.
So in odd dimensions,
This
odd dimensions, there are no anomaly.
So
psi would just be a phase.
no, but the Z will be there. There will be some like del omega of Z will be 0. So you can take some Z which satisfies this equation. You can still solve some Z. It's not like the Z is 0.
But you don't know how it becomes imaginary. I mean, what is the physical interpretation of? So you started off by writing psi equal to e to the power if, and you were solving it.
Yes, solving it.
But in odd dimensions, if you try to solve it, all the things in f would be real numbers.
No, not necessarily. Like I am saying this. We have got this is as a pure phase factor, but then the solution of the x0 term e to the power ix0, that is not unique. That is not unique, and you can take the real part of this quantity always, even if it is some complex number. the imaginary phase will cancel out, but you can always take the real part, and that you can put into mod psi square. Like,
Sorry, it is not unique. What is it that fixes it? I mean, it's some arbitrary thing.
no, okay. So here is this catch. So the point is, if you different Z CFT means different states. So that we are interpreting because Z is not unique. So if I give you different CFT partition function, that will give you different states. And so in that sense, it is not unique. But they obey some common equation, like some omega del omega Z equal to some anomaly for even and equal to 0 for odd. Okay. Okay. Cool. Okay. Okay. So I am just so we have started from this HI equal to 0 and HSI equal to 0, and now we have boiled down to this equation omega del omega Z equal to some ADZ, and also this we have, okay, let me write down in the full the variables here. So this becomes 2I Gij del Gij minus del chi del chi, this Z equal to some ADZ, and also we have found this 2 square root of delta I 1 by square root G del Gij minus Gij del I chi. So this is this Hi equal to 0, the special diffeomorphism invariance here. This is the momentum constant part, and this is the Hamiltonian constant part, like reduced to some simple equation here. Now I will tell you, like these are the same equations you get for a partition function in d-dimensional CFT. Okay, let me tell you how. So Z is a function of Gij and chi, and so if we are now everywhere in d dimension, okay, some d dimensional space time, so you can actually like perform some Weyl transformation and some special diffeomorphism on these variables on this d-dimensional surface. And these transformations are defined by the following: the diffeomorphism of the metric and this field are just some Lie derivative. D plus 1 the de Sitter, but we have, but the canonical analysis like reduced one dimension and do everything on this slice. Like for like we are trying to specify the states, and the states are like defined on the slice here in this canonical analysis. So this is, so this special diffeomorphism is just this some Lie derivative, and also we have this Gij equal to 2 phi Gij. This is the Weyl transformation I am putting on the metric, and also this chi has a scaling dimension, and that scaling dimension appears in the Weyl transformation like del phi chi. So this is some standard Weyl transformation I can perform on these fields on the d-dimensional surface. Now what I am claiming that like if you take del phi of change of the some, you do some you change your Z with these variables, like you perform both Xi and phi on your variables, and then you make a Z out of these variables, and you are trying to calculate the change of Z with respect to this Weyl and diff transformation, and you take a derivative with respect to the parameter, Weyl transformation parameter. I am claiming that this will give you these equations where this like with this appropriate anomaly, like this will be non-zero something, and this will have some anomaly term, and I am claiming like if you take this like this derivative with this parameter, you will get this equation. Okay, and similarly if you take this guy, sorry, here it is chi, sorry, I am mistaken. Now you can also like take the change of Z, and you can also take the derivative of Xi parameter. But I am claiming like this will give me this equation. So in that sense, this CFT partition function, this anomaly is important here. This particular anomaly term is important here, which appears here. Like I am saying, under this Weyl transformation, it will capture an anomaly, and that will be deflected there with the particular choice of I and everything. Now, what I am claiming here, so this Z is actually sum e to the power d dx chi and phi with this metric. So if you take some Z like this with this particular choice of anomaly, they are going to satisfy these two equations, and they are my valid states. And but these are not really CFT. Okay, CFT has some other, like CFT, we don't know whether it's unitary, local, anything. So we are saying CFT only from the perspective they satisfy this kind of word identities. In that sense, we are claiming these are CFTs, and one particular like point is that the anomaly is imaginary. So this is some weird kind of CFT, but the point is we already know this kind of CFT. Okay, like CFT partition function. So this one can get when one calculate Hartley-Hawking wave functions. Okay, so just to give you an example, like say we are trying to calculate some Hartley-Hawking wave function for a de Sitter theory. Say we have a de Sitter theory. So Maldacena gave us a prescription, which is like now write, you have this de Sitter. Now take an analytic continuation of your de Sitter, okay, of your de Sitter time. Say I am taking some de Sitter time, time coordinate. I am taking some like with this I of your say radius here. Radius corresponds to the anti-de Sitter, and also you take this L de Sitter to I of L anti-de Sitter. If you take this kind of analytic continuation, you will land with Euclidean ADS. Okay, and now what you can do, like what people in holography renovation they do, they take this radial slices here. So this is my anti-de Sitter with this boundary. They take this radial slice here, and they are trying to calculate this partition function of your Euclidean ADS with this particular boundary condition here. Boundary condition means like they are specifying this metric and field here, and you can get some partition function which is function of this Gij and chi. Now you have some solution. Now we can analytically continue that to again the de Sitter with this thing. Now if you remember the central charge and everything, they have some L de Sitter or L anti-de Sitter, like L anti-de Sitter, like in Brown-Henry central charge they have one L anti-de Sitter. So if you are now trying to analytically continue anti-de Sitter to de Sitter, you have some factor of I, and that is reflecting here. This anomaly is imaginary. So like if you are trying to calculate some Hartley-Hawking wave functional for a given de Sitter theory, you will land into this kind of like Z's which obey these equations. Okay. Now, so okay, you can ask this question. Okay, it is already known Hartley-Hawking is solutions. So what are the new things we have done? So the new things we have done, we are claiming that Hartley-Hawking is one particular state. Given a de Sitter theory, Hartley-Hawking is one particular state. Yeah, de Sitter for there is no anomaly. Yes, like it is 3 plus 1, 3 is 3. Yes, yeah. So now, but now one already we know that psi HH has this form. They also have this divergent factor here, like this e to the, if you calculate carefully, they have also this divergent factor which they like remove with this holographic renormalization. They add the negative of it to this partition function and they cancel it, and they get this ZCFT as the renormalized part. But if you want to analytically continue to de Sitter, you don't have to cancel that. So this divergent factor is there, and this divergent factor is just the e to the power is. So this has this factor Z here. Okay. Now the point is what we are saying new. We are saying all other states have this form. So if you take some other ZCFT which is satisfying these same equations, okay, then it is a valid state. So one particular schematic example I can give you. Let's take two different bulk theory. Okay, let's take two different bulk theory. Say I have bulk 1 and then I have bulk 2. Bulk theory means some de Sitter theory, and for that and I am choosing this theory such that the e to the power is factors are same. So I have this e to the power is, and then we have some z1 and some z2. And now the point is that this z1 and z2, they are going to satisfy the same word identities. So you can think this z2 is also a valid state in the bulk theory 1. Okay, so you can think like the space of the, you can naively think the space of all possible states might be the space of all consistent Hartley-Hawking wave functionals of different bulk theory. You can think like that. Okay, this is some thing we are proposing, and then okay, is everything fine? Okay. Like what we are thinking is that there all the possible Hartley-Hawking states correspond to different theories. Like they may correspond to a complete basis. You can think like that.
We are supposed to average over all these wave functions.
Not average. I want to say like superposition. Like you can think like, but like in general one cannot add partition functions. Like partition, this is ill-defined. But now, as I was saying, like ADS in the boundary we are getting the partition functions in the boundary. But in the de Sitter, when you are solving these constraints, we are getting, this is the Cauchy slice, they are not radial slice. So Cauchy slice we are getting the states. Cauchy slice, if you solve the constraints, we are getting the states. And we know in quantum mechanics we can add states. So you can add these two different partition functions and get a new state. But that may not correspond to some bulk theory also. Like the superposition of two Z1 may not also correspond to some bulk theory. Yeah. So okay. So after this point, is everything clear?
So these are all normalized?
Okay, norm is, okay, norm we have to define. We did not define the norm. Normally very important for us, because we will see like defining norm is a bit tricky business. Like we have to take care of this. We have to divide by the gauge group basically. Because you see these jades are like, the jades are catching some Weyl anomaly, but mod j square that will appear in mod psi square, that is almost Weyl invariant. Like there can be some measure which will change up, like if you define some measure in this inner product, the measure can catch some Weyl anomaly, but up to that, like everything is Weyl invariant. So you have to divide by this volume of defined Weyl group, and you have to do this consistent Faddeev-Popov gauge fixing and etc. And you will get some correlation function after that. So yeah. So
this interpretation of Z as a partition function, this only works for even.
No, not for all D.
But how are you going to check it for odd D?
No, odd D there is in CFT there is no anomaly, na? So so in the CFT I am saying this partition function are defined Weyl invariant. So because there is no Weyl anomaly, I am saying.
But in even dimensions, I could imagine that categorizing the theories using the anomaly.
Okay. Yes. Yes.
In odd dimensions, you can't do that.
No, odd dimensions this part is just 0. Like in odd dimension this part is just 0. So you can think we have a partition function which is like both defined Weyl invariant. Like but you can always like I am saying, like in de Sitter 4 or like de Sitter 4 like d equal to 3, you can calculate some ZCFT, but like what I mean, you can calculate some Hartley-Hawking vacuum.
But there could be, I mean, in principle there could be infinite number of CFTs, right?
Yes. Like in this way of looking at the states, like the dimension of Hilbert space seems infinite. I agree. You may say like there are some other constraints, like that does not come from Wheeler-DeWitt, but there can be some other constraints which restricts the size of the Hilbert space. Yeah, you are right. Like, but that does not come from this Wheeler-DeWitt perspective.
But it seems like there is a difference between, okay, I mean, central charges usually, if you think of them as measuring some degrees of freedom, you imagine that you can count them. So there's a difference between accountably infinite versus
Oh, okay.
an uncountably infinite.
Okay, okay, okay,
Right, so
okay. Yeah. Okay, I am not sure about the subtleties about odd dimension, but okay, we can. Okay, but what are you trying to say? Like these are only the constant of Wheeler-DeWitt equation. There can be some other constants, some unitarity constants or anything. But as of now, this CFT does not seem any unitarity or anything. Okay, so what is the time? Okay, maybe in.
is this a good place to stop?
Yeah, we can stop. Yeah, we can stop now and.
And we can continue on.
Okay. So is there any question you can ask me? Yeah. So yeah, just to summarize, like we are trying to like get the states in the quantum gravity, and I was saying that states must satisfy the constants, and we have derived the constants, and the main like problem is the Wheeler-DeWitt equation, the Hamiltonian constants, and this and what we are saying that we have now the solutions of the Hamiltonian constants. Hartley-Hawking is always a solution, but what we are saying more that all the states have this form. You can think like different like Hartley-Hawking states of different theories are like in the states in the Hilbert space. So here now the next term, like I will try to like analyze this Z. Like we can now up to this point there is one perturbation parameter omega. We have perturbed around omega, large omega. But we did not touch this kappa, this G Newton. Here, next I will expand the G Newton. I will write explicitly the form of Z, and then we will understand the inner product, and then we can understand the cosmological correlator, etc. So, okay, thank you very much. Okay, thank you. Of your ADS, the CFT of your ADS CFT.
Oh.
So that's the prescription Maldacena gave us. Like,
so that CFT is categorized only by the central charge.
Central charge as per event dimension and
So
and odd dimension is just 0. Yes. So it is a prescription that Maldacena gave us, and so in that way you can think these are some CFT, but we don't know. Well, okay, I don't know whether these are some local unitary CFT or anything. Yeah.
So any ADS CFT you can just.
Yeah, you can just analytically continue it. So yeah, but I don't know what are the classification of those. Yeah, I have no idea.
Okay.
Thank you.
So next on Friday we'll meet in the meeting room.
2 p.m.
I think meeting room will be better, no? I mean, because it's a smaller.
What is setting up this? I don't
Oh, I see. Okay. Yeah, I don't know if this is recorded. Okay.
Okay, thanks.
Yeah,